So we're going to finish the semester with just a tour through really useful functions. We've seen a few of these before, but we're going to go into some more detail. And right now we're going to talk about power functions. And that includes something that's pretty familiar from our algebra studies, which is monomials, things like x to the fourth, negative x to the fifth, minus 17x to the 12th. Those are just polynomials with one term. It also includes, we're not going to focus on them right now, it also includes power functions where the power might be unusual, like 1/3, which is secretly, of course, a root function. We're going to separate those out. And also, because they have rather different behavior, negative powers, we're going to separate those out as well. But those technically are power functions. But right now we're going to look at non-negative integer exponents in this video. And so they really are going to be just another name for monomials. I want to really highlight that these are very different from exponential functions. And so if you've got, let's say, g of x, notice here we've got something being raised to a power, and the variable is in the base, and the power is a number. It's a constant. It doesn't vary. It's not a variable. In contrast, if you had like 2 to the x, or maybe more generally some constant times like 10, ooh, that doesn't look good, constant times 10 to the x, that would be an exponential function where the variable is in the exponent slot. These are very, very different. And we're generally going to wait until trig precal to really focus on those. They're not, we could do them right now, but we wait for a while. So I want to highlight the difference there. So we're looking at stuff where the base is the variable and the exponent is constant. And again, these aren't really new, they're just a new perspective. Okay. And of course, a lot of what we're focusing on right now, partly we're focusing on the idea that this is a function, that it inputs an x and outputs an f of x. And to get some intuition about that, we, of course, want to look at the graphs of these things. So I'm going to go over to Desmos, and let's take a look at some graphs. We know the most basic one of these, x squared, parabola. We've been focusing on that in the last couple days. That will never cease being really, really important, but we want to go beyond that. And we've already seen a little bit. X cubed, that's been in our library, our toolkit, whatever metaphor you want to use. And notice that because the exponent is odd, it's quite different from x squared. X squared goes positive in both directions. X cubed goes negative when x is negative, because a negative multiplied by itself 3 times stays negative. So that's a really important distinction, is whether it's up, up, or down, up, like that. And as we increase the power, we can see that even powers both have that up, up structure, and odd powers have that down, up structure. So that's part of what we're going to focus on. Also, as you go, let me zoom in a little bit more. As you go up in the power, it gets a little bit sort of more extreme, like x to the 10th, for example. If you think the parabola's job is to be steep on the sides and flat-ish in the middle, like if we go back to the parabola, well, not very flat, but temporarily, just right here, it's horizontal, then x to the 10th does that job much, much better. It's very steep over here, and it's quite flat in the middle, right? And that's just because of arithmetic. It's things like 0.1 to the 10th power. That's a very small number. We even need scientific notation for that, because it's 0.0000001. So, and of course, if you just take a measly 2 to the 10, that's 1,000. That's indicating that even if I scrunch this way down in scale, whoa, it's blowing up really, really fast. I have to scrunch that scale really, really far down to even see what f of 2 is going to be. Okay, so maybe take it back to my home screen. Okay, zoom in. So the graph shape for it, and let's see, what else can we do? We could, of course, multiply it by a number. Let's take it back to something that's not so extreme. Let's say x cubed. We could multiply that by a number in front. That still counts as a power function, and that's going to make it either more steep or less steep. And the key thing I want to focus on right here is simply what happens when you multiply by a negative. Not new. We know multiplying by a negative flips it upside down. And so that means that, for example, when x is negative, we're taking negative of a negative cubed. So there's 3 negatives coming from cubing the negative and another, so that ends up being positive. So now it's up and then down as you go from left to right. Okay. So what we see is that for a power function to get the general shape, what matters is whether the power, this exponent is even or odd, and whether you're multiplying by a negative or not. And you can all just reduce it down to arithmetic. If you want to know what happens on the left or right, just think about what happens with negative numbers or positive numbers raised to the various powers. So let's summarize that. Okay, so the graph shape is going to be for even exponent, it's going to be, it goes in the same direction as we go left or right. So it either goes up, up, or down, down. And so, for example, f of x equals 7x to the 4th. That's going to be up, up. And f of x equals minus 7x to the 4th. It's going to be down, down. Odd exponent goes in opposite directions. And so if f of x, I guess I'll keep using f just for fun. If that's like 15x to the 5th, that's going to be down, up. And f of x equals minus 15x to the 5th. It's going to be up, down. Okay. And that's nice to know, but what we're more interested in than just the pure power functions is we're going to be interested in combining those. And let me just say, so this is basically what I've just been saying. Let me just give the terminology here. What we're looking at is called end behavior. And that is not what happens for small values of x, but what happens for large values of x. So for example, we're going to make it a little more complicated in a second, but for example, let's go back to x cubed, and suppose it was like 0.0001 x cubed. Now, if I'm putting small x's into here, it looks like it does absolutely nothing, because that x cubed can't overpower that very small coefficient in front there. But if I zoom out in the x variable, notice I'm trying to zoom out only in x. So I'm changing the x scale. Now what we start seeing is as soon as we get to 20, 40, we start recovering that x cubed shape. And when x gets really, really big, then we get that familiar shape that f of x gets big and negative when x is negative, and f of x is big as positive when x is positive. So sometimes that behavior that we know should be there, it might only show up when x is rather large. And that's why it's called the end behavior of the function. And the cool thing is that even if we go to more general polynomial functions, then it turns out the end behavior is still easy. So what we're going to be looking at in the next few days is a few of the details of what polynomial graphs look like. Getting absolutely all the details by hand is hard. It's a good place for using a calculator in a lot of cases. But one of the things that's easiest to predict is this end behavior. What happens when x is really, really large, either positive or negative? So let me see. Let me copy this over. Let me see if I can copy and paste it to Desmos here. So let's look at this function. Oh, that's good. Okay. So let's say f of x was not just x cubed, a power function with an exponent 3, but it's a full-fledged polynomial with some other some other coefficients. And wow, that's kind of a weird graph. Okay. We just have this, what looks like a vertical line around 6. What the heck is going on there? Let's zoom out in the y variable first to figure out. Oh, okay. Okay. So now I can see more clearly what's going on here. I've got something that's moderately complicated. Now, this certainly could get much more complicated if this polynomial had a higher degree. It's moderately complicated. It's got a little bit of a change of direction, a couple of changes of direction, little bendy. But when I zoom out, what I start seeing is that characteristic x cubed shape. And that minus 100 seems to have a pretty big effect. That gave a pretty big value when x is equal to 0. So notice the y-intercept of this graph is just exactly the constant term. That's a nice thing to know, because if you plug in x equals 0, all you will get is what's over here. So that's sort of one extreme. Putting in x equals 0, you get just this term. But the other extreme is what happens when I put in x equals large values either way. And my claim is that that's always going to be dominated by this term here. So let me even make it a little more extreme. Let me actually make these like really, really big. Now, it seems like I'm really changing the behavior, but if I zoom out, oops, I zoomed out the wrong way, yeah. Oh, look at that. Look at that. Let's see, oh. There we go. I'm seeing that same kind of cubic shape where I go up, I have this little wiggle, and then I keep going up again. And what it's telling me is that as long as I put in big values for, there we go. Let's see if I can massage it a little bit. There we go. As long as I put in really big values for x, I'm getting that familiar cubic shape. What's going on there is that, for example, if x is 200, right, what are we going to get? We're going to get that first term, 2 times 200 cubed. That's a really, really big number. Now, 150 times 200 squared, it's pretty big, but it's starting to be outpaced by that cubic. And the 3,500, even though it's got a big coefficient, ooh, that's falling behind. If I zoom out even more, let's see, squish that, squish that, squish that. Then it becomes much, much more like the absolute classic x cubed shape. So let's actually compare it. I'm going to graph just 2x cubed and nothing else. Oops. Wow, those are really similar. Okay, it's very hard to tell the difference between these two graphs when x gets really, really, really big. So what's happening here is that if you want to look at the end behavior of a function, you want to imagine putting x's in that are really, really big. And eventually, even if the coefficients of these lower degree terms are pretty large, eventually who's going to win is that leading term. And so that's something we can summarize very well. The end behavior of a polynomial function is always identical to that of its leading term. Okay, so another example would be, let's say, f of x equals minus x to the fifth plus like 10,000 x to the fourth minus 2,000 x cubed plus 120,500. When you've got small values of x, these guys are going to matter a lot, and it's going to be pretty complicated. But when I look at the end behavior, and I'll show you a little bit of terminology, a little notation for that, as x goes to infinity, which is just a nice way to say x, I'm putting in x's that are bigger and bigger and bigger and bigger. So we're not actually infinity is not a number here, it's a direction that we're sending x off into. It just says when x gets bigger and bigger and bigger, f of x, it's going to behave exactly like minus 6x to the fifth. Well, if x is positive, then the x to the fifth is positive, but the explicit minus sign is going to say that's going to be bigger and bigger negative numbers. So this is symbolism for as x increases without bound, just keep going and going and going and see what happens. F of x decreases without bound. In other words, becomes more and more negative. Okay. And what's the other end behavior? As x goes to minus infinity, that's putting in bigger and bigger negative numbers. You want to think of that on the graph as going further and further left and seeing. So you're putting in x values that are further and further and further left, and you're seeing what the y values do. Then in this case, because that's a minus x to the fifth, minus 6x to the fifth, we're going to have f of x goes to, well, x is negative. It's an odd power that stays negative, but then the minus flips it, and that's going to go to infinity. If you really want to emphasize it, you could put a plus infinity here, but people tend not to do that because we don't usually put a plus in front of positive numbers. But if you want to emphasize it, sometimes it's a nice thing to do. Okay, so this is a very nice little notation. It fits in very well with stuff we do in the next few years called limits. But for us right now, it's just a nice way to symbolize this bit more cumbersome English language statement.